So, my name is Minghan Xia. I'm from the Kubernetes networking team. And today I'm just going to briefly go over the network fundamentals in Kubernetes. So before I start, I wanted to get to know how many backgrounds and how many people are working in this field. So how many of you have experience with Docker? Okay. How many of you have experience with Kubernetes? Okay. So any of you knows how the networking piece in Kubernetes works, like under the hood? Cool. So we have a very diverse crowd here. So before we jump into Kubernetes networking, we do a quick review of the Docker networking. So this is probably a few months old, but with their new lib network coming out, but this is the still default networking provided with Docker. So start with Docker start. So users type Docker start, then you have a Docker daemon running on your host. And the Docker daemon, we're going to create a Linux bridge. By default, it's a Docker 0. And then you will have a subnet attached to the bridge. And a Linux bridge is a Linux virtual switch, L2 virtual switch. So, and if one user says Docker run, then the Docker daemon will create a Docker container and then hook up the Docker container with a pair of VF, one on the bridge and the other on the inside the Docker container. So that's basically how Docker daemon controls provided networking piece for the Docker containers. So if you run another one, then you're going to hook up another pair. And these two, when they're on the same host, they have different IPs. So when it comes to multiple hosts, you may end up with containers in different hosts with the same IP. You can see we have 3 hosts, and this IP address is clashed. This means that the container IPs is not routable inside your cluster. Okay, so to route that, you need NATs. So for instance, you wanted to expose the container A, you have to expose a host port. And for instance, the container A has the port 3306, and then expose a host port 9376. And then so that container C could hit container A through the host port 9378 of the host on the left-hand side. So that's the default way Docker provides the networking piece. So that's not very ideal. You have to deal with the mapping between containers and the host ports, and then you have to do service discovery based on that, and then you lose all the benefit with routable L3 IPs. So that's not ideal. So we rejected that. So in the Kubernetes world, we assume that the IPs of the containers are routable within the cluster, globally within the cluster. And we don't need NATing to reach each other. We just directly hit the IP address of the container. So I lie a little bit because we are not in Kubernetes, we are not dealing with containers, but rather pods. So I'm gonna explain what's pod in Kubernetes later. Okay, and we also don't need to babysitting the port numbers and maintain the mapping, et cetera, et cetera. So so in summary, the fundamental requirement for Kubernetes is that the IPs of pods are L3 routable, and it can be done by underlay or overlay networking. So underlay means that if for instance, the cloud network fabric already provides the programmable routes, then use that, or you have other networking solutions that provide overlay networking. Okay, so this is how it looks like. So each host, each node in the Kubernetes cluster has a different IP range you can use, and then all the pods has a unique IP so that they can talk to each other. So how this works, how to implement, or what's the detail under the hood. So for Kubernetes networking to work, there's a bunch of network providers that came forward. So, for instance, on GKE or GC or AWS, so these are the Google Cloud platforms and Amazon Cloud platforms. There's advanced routing features. So basically, you can define like I want a subnet, all the traffic to this subnet routed to a specific VM. You can program that on this cloud platform. Or you can use other open source cloud providers. Like for instance, we enable Flannel out of the box. Is experimental currently, so you can try that. You can spawn up your Kubernetes cluster with network provider equals to Flannel, and then it's gonna give you Flannel. We're gonna provide a network fabric under the hood. So just a little bit background for Flannel. So basically, it's a Core OS. They built that, and then it's backed by a key value store, and then it maintains the mapping of what subnet belongs to which host, just that, and then the agents encapsulate the packets and send to the right host. That's yeah. So come back to pods. So it seems like a lot of people here are new to Kubernetes. So the guys who are veterans, so bear with me. So pods are a small group of containers and volumes. They are tightly coupled. They come, live, and die together. Okay. They share all the namespaces, the network namespaces, IPC namespaces. Like they also share IPs. Okay. So on the right-hand side, there's a example of pod. So for instance, you can, in this pod, there's two containers. The gear icon is for the container. So you have one container is file puller. It pulls content from somewhere and store the content into a volume. The volume can be a persistent disk provisioned by a cloud provider, or just a directory inside on the node. So the other container, web server, just grab that content in the volume, in the shared volume, and then serve to the customer. That's an example of the pod. So how does the pod, how we implement the pod for the networking to work? Like these two containers has one shared IP, right? So what's under the hood? So in Docker, there's no concept of a pod. There are minimum unit of resources containers. So to work around that, we created an infra container. The infra container does nothing. It's very lightweight. It just start and pause. Its only job is to maintain the network namespaces, the IPC names, all the namespaces required for other containers. So, and other user-defined containers share the same namespace with this infra pod. So when a user-defined, like for instance, a container C1 dies or it somehow crashes, the kubelet would just restart it or recreate it. But if the infra container dies, the whole pod needs to be teared down and then recreated. Okay, that's how the pod is implemented. So services. So this is another abstraction in Kubernetes. So since pod can die and live like in a very short amount of time, and its IP is invariable. So when clients want to access those pods, it may not be there. It may be there, it may not be there. So you want to have a static access point. So Kubernetes provides a concept of service, which provides a static access point. It's basically a virtual IP. And when the client hitting that virtual IP is gonna get randomized to hit one of the backend pods. So a quick about the pods and the services. So I have pre-spawned. Let me let me increase the font. So I have pre-spawned a Kubernetes cluster on GCE. So the kubectl is our command line interface to interact with the cluster. So see, the cluster info is running somewhere, and all the kube system services are running somewhere else. And I have, because I'm bad at talking and typing at the same time, so I'm gonna run a script, and then it's gonna type for me. And then I'm assure you that's a live demo and not a like a video. So first, we're gonna set up the namespaces. So Kubernetes has a concept of namespaces that provides the isolation of resources. You can, each service and pods belongs to a namespace. And right now you can see I only have two namespaces, default and kube system. Kube system is the namespaces that holds all the like the required resources that new Kubernetes needs to run the cluster. So here we created namespace. So as you can see, the definition language is very simple. It's just kind namespace and the metadata name demos. And we create the namespace. Then we have a namespace demos created. Okay. So now goes into the service demo. First, we want to run some pods. So because I don't want to create the pods one by one, I'm gonna utilize one of the object in Kubernetes called deployment. It's gonna massively manage the containers for me. So here I specify in the namespace demos, I want to run host names. Means that the name of this deployment, and with the image of serve hostname 1.1, and runs it in 5 pods with 5 replicas. Okay, let's see. Then we have 5 pods in the namespace demo we just created, and you can see their age is like 30. Just happened now. Okay, then we expose these pods through service using the same command line tool, expose deployment host names, because the host names is is the name of our deployment, and then using pod 80 on each pod. So a little bit explanation of what does the image do. The serve host name just spawn up a web server, and then you hit the pod 80, and then it's going to reply with the host name of the web server. It's simple as that. So after we created a service, then we can take a look at the service. SVC is short for services. So and then the service has the same name, host names, and you can see there's like 5 endpoints, which pointing to each of the pod. So next, we're going to access the service IP. So we have the IP of the service, and then we log on to the GCE, my GCE compute. This is the Kubernetes minion is one of my Kubernetes node in the cluster. And then on the node, we execute a command, which is just curl the service IP 10 times, and then see the result. And you can see you have 10 line of response. Each line is a hosting for the serving pod, and you can see it's roughly it's very different. Probably roughly 5 of them. So probably hitting 10 times is not enough. So we decided to hit 500 times, and accumulate the counts. Okay. So on the left column is the number of response, and the right column is the actual response. So you can see it's roughly evenly distributed among 5 different pods that we just created in using the deployment. Okay, so this concludes this demo. So let's go back. So how does this work? How does this work under the hood? So it's done by the kube proxy. It's the kube proxy that does the heavy lifting. And we are using the second version of the kube proxies, which is the IP tables. We have a user space kube proxy, which is nice and slow. And we have a new one, using IP tables. So what happened is each of the node inside the Kubernetes cluster runs a kube proxy. And the kube proxy establishes a watch to the API server, and it will get notified as whenever there's a service update or endpoint update. And when the user says kubectl run, then the API server is going to run 3 pods. And when the user says kubectl expose, then the kube proxy finds out that there's a new service. Then it's going to configure its local IP table rules to reflect that. But in the beginning, there's no endpoint for the service, and the VIP gets nowhere. So at the beginning, when there's no endpoints, when you access the VIP, it's just going to get dropped. So when there's new endpoints come in, and kube proxy will again configure the local IP tables rules and make it act like a randomizer. So when a client on a node tries to access the VIP, it's going to go through this randomized randomizer, and then it's going to land on one of the backend pod. The probability is distributed evenly. Okay, this is how it works under the hood. And so in summary, servers are just an abstraction. So how we implement it is implementation detail. We may try something new, like other than IP tables. We may try IPAVS. And one day we may make the kube proxy pluggable and make the user and the community to plug in more configured, customized kube proxy to work with their own network fabric. Okay. So next is the kubedns. So by default now, Kubernetes cluster comes with a kubedns. It's backed by a Sky DNS with customized, we would customize a little bit and then make it reflect what we need. So for instance, the Kubernetes service is first created. It's by default, and then it's for accessing the API server. And this is you can access the Kubernetes service on any node just hitting Kubernetes, or Kubernetes.default. Default is the namespace, or the full name, which is Kubernetes default.svc.cluster.local. The last piece, the cluster.local, is configurable. You can configure any domain name you like. You can even configure google.com. So it's just not going to route. Okay. So say you have a service full. You have a question? Yeah, you can feel free to interrupt me.
Yeah, actually, this is about the previous slide.
Okay.
Where the one before that, where the client is going to be accessing the services that are provided by those 3 pods on the right.
Yes.
How does the, I think I remember something about environment variables that use the name of the service, like to service host and service port. Is that how a client knows about that service?
We will talk about it later. You may confuse with the DNS piece, so we'll get there eventually.
If anyone has a question, please.
Thank you.
I'll also repeat the question just so that people will watch on
I see. Okay. So how does this kubedns works? So it's again a watch. So it runs in a pod within the Kubernetes cluster. That's what the kube system namespace host. This is one of the tenant in it. So the kubedns establish a watch to the API server again on the services, and then it's going to inject the name server into all the pod it created inside the cluster. And this address 10.0.0.10 is the static service address for the kubedns. So whenever there's a DNS lookup request, it's gonna goes to 10.0.0.10 within the cluster. It's gonna hit kubedns. Okay, so it's time for another demo. All right. So remember our hostname service we just created. It's here, still there, and with the same cluster IP. And we're gonna create a pod just to access the service. So this pod is, I name it curl pod because what it does is basically curl. It's a very lightweight image with BusyBox as a base and then some other utils inside. So I create this pod. So the curl pod is created. Then let's see what happens if we do an NS lookup inside the curl pod. So this is the command line that to execute a command inside the curl pod. So this is a kubectl namespace and exec, and then the pod name, which is the curl pod we just created, and the command, which is then ns lookup host names, which is the service we created before. Then you can see the IP is 10.0.242, and then it's the same IP. And more ns lookup. So hostnames.demos, that's adding the namespaces, and also the full domain name, hostname.demos.svc.cluster.local. And then we'll try to reach the service inside the pod. So again, using the execute command, execute a command inside the curl pod, which is just curl the hostnames.demo, which is the name for the service. Then we get a response. One of the backend ports serves the request. Okay, so what just happened? So here, putting it all together, when you try to reach a service inside a pod, this is what happened. So in the pod, the name server is dedicated to Kube's DNS, and since it doesn't know the service name, doesn't know what's the IP of the service name, then it asks the name server. And kubedns returns the service IP, and then again this client tried to reach the service through the VIP, the service VIP. And then the service VIP goes through a randomizer, and then and the randomizer pick one of the pod, and the pod and the request got routed by some programmable network fabric or overlay network that decide, okay, this address will be sent to a node X, and then eventually hits to the pod on a specific node.
Is the SkyDNS running on every host? Is it distributed or?
Okay, the question is SkyDNS running on every host or is it distributed? The answer is that we only have, by default, it only have one pod running SkyDNS. So the whole cluster only has one SkyDNS pod serving the NS lookup. Okay. Any other try? Okay. So we get a response, and then it got come back, and then it got netted again, and then we got the response. So what we just talked about are all accessing and communicating within the cluster. So how about what if I want to connect from outside the cluster. So by default, the service IPs are only available inside the cluster. So if you wanted to, and we have a bunch of service types. The default one is the cluster IP one. It does not, it just gives you a cluster IP accessible within the cluster. And the second type is node port. It will expose a port on each of the node. And whenever you hit this port on any node inside the cluster, it will get rerouted to the service. And the other one is the load balancer one. It will actually provision a cloud load balancer and then use the cloud load balancer to route the traffic to the service. So maybe a little.
Is the load balancer only for HTTP or also support TCP?
Here, good question. The question is the load balancer supports TCP or HTTP? So here we are talking about services. The services load balancers are only L3 or L4, so it supports TCP. Okay, but we're gonna talk about HTTP load balancer later. Okay. We also support like DIY load balancer solutions. You can come in and swap whatever. You don't want to use the cloud provider's load balancer, it's okay. And some more demos. So in this demo, on the left-hand side, we're gonna keep hitting the service we just created, the hostname service, and you will see the response coming up. And on the right-hand side, we just adjust the replica of this deployment to 1. So it means that there's only one pod serving the traffic at this time. So you can see the response are the same because there's only one pod. And where we resize the hostname deployment to 2, then there will be 2 pods serving the traffic. So you can see occasionally there's 2 different responses. Okay. Scale it back to 5, and then you will see responses gets very different. So now we replace the service we created, the hostname service. The default type is cluster IP, and we are not happy about it. Then we substitute with load balancer. Then you will actually go provision a cloud load balancer and hook up the rest. It's gonna take a while, so we'll just get and see if it's. So it's not ready yet, so we're gonna come back to the presentation and later we'll check if the load balancer is ready. So what's gonna be new is ingress, which is the gentleman just asked about. It stands for the L7 load balancer in the Kubernetes cluster. So it supports the usual functionality as for a HTTP load balancer like SSL, URL path, URL mapping, host headers, and things like that. So say you have a client and then you have a domain and you wanted to map different URLs to different serving pods. You can do it with ingress, which is L7 load balancer equivalent in Kubernetes cluster. Okay, and also the network plugins. So we are in the process of putting all the network traffic, all logic into plugins, and we define common operation interfaces so that we wanted to level the playing ground so that anyone who wants to be a network provider of Kubernetes can come in and just implement those interfaces. So we are in the process of that. And then we are not using the Docker lib network. So Tim has a long blog explaining why we cannot use it. Go check it out. and network isolation. So network SIG in the Kubernetes community is driving this effort. So say you are you wanted to define the traffic pattern, or basically, for instance, you have the front end pod. You don't want it to access the back end pod directly. You only allow it to access the mid-tier pod. You can do that with the network isolation. Okay, let's come back and see if our, oops. Okay, let me, okay, we got a external IP provision. Okay, and we can try to hit it. This is an external IP served by a cloud load balancer in GCE. And this is the response we got. And then we can hit it more times. Yeah, you see a different backend served my request just now. Okay. So that concludes my presentation. So Kubernetes is open, so come join us. And network is hard, so help guide us. So thank you. Okay.
So the first question is L7 ingress. Is it relying on cloud provider, or it's completely internal to Kubernetes?
So the question is the L7, the ingress object, is it rely on a cloud provider or is it internal? Okay. So the short answer is it is an internal object. It's an abstraction within the Kubernetes. Who serves it, or when it depends on your network environment, right? For instance, if my cluster runs on GCE, then Google Cloud provides the L7 load balancer. But yes, you need to hook up your local network environment with the ingress object in Kubernetes.
What does that mean?
It means that you somehow have to implement the common interfaces that require by ingress to function. Like for instance, the ingress supports like provisioning a load balancer, then you have to have an interface that ingress can call out to get a load balancer provision.
Another question is why IP is not included in pod spec. In pod spec, and it's private, it's in pod.
That's related to the IPAM, right? So if I mean, it's a very dynamic environment inside the cluster. You don't want to. I think there's a way to specify the IP. I forgot. I can answer this question later. I think there's a way to like pinpoint the IP for the pod. Yeah.
Question about the kube proxy, and you showed me in the demo that you hit several times, you hit the different pods, right?
Yes.
So how did you work this to for a service like WebSocket to make sure you always hit the same pod when you start a socket?
So there's a field in the service spec. It's called a session affinity. So basically, it defines the stickiness of your session. So if you want to hit on the same pod. Oh, by the way, the randomization only happens on the connection establishment time. So if your connection is established, then you won't worry about hitting the different backend, right? So if you have multiple connections, then you can use the session affinity field and then define the stickiness. And then you can basically, at a period of the time, then you will only hit one of the backend pod. That's basically how it works.
I had a question actually for our audience. As you said, it is hard. Networking is hard. Google is solving a lot of the issues. I'm wondering if anyone is actually running this in the data center on their network. Thanks.
Another question, maybe question. So what about networking containers within a pod or across pods? So I understand as a service, and I understand the Vipin stuff, but within containers, within a pod as well as across pods.
Okay, good question. So the question is, how is the communication happen between the pods, right? So get back to the very previous slides. So basically, this is a mini cluster, right? For instance, you wanted to have this red pod hitting the yellow pod here, right? So then you just specify the IP of the yellow pod. What happened is that the underlying network fabric will pick up that IP and then decide where to route it, right? For instance, on GCE, the network fabric is programmable. Then you can specify, okay, this subnet range for all the network traffic going to that subnet range routed to this box. And once it reaches to that box, then the local the Linux bridge will take over and then decide, okay, this IP hits my Linux bridge, and then send it to the bridge. And then on the other side, the container, because they have an IP, then they identify, okay, this packet is for me, then it takes it from the bridge.
Question is more within the pod. Let's say there are two containers within a pod.
Okay.
If they have to talk to each other, is there a service discovery? How do they have to talk to each other? Or what's the mechanism of it? Once you have an API, the routing is pretty clear.
Okay.
So,
So you mean this? You mean this way? You want to communicate? And you mean basically the containers? You mean the containers inside the pod? You wanted to talk to each other. So you can multiple ways. You can have different ports, right? You can have IPC, basically inter-processing communication, using pipes and whatnot, and a bunch of techniques, and share memory or share volume like this. So that's basically how you handle it. Yeah, because that's a runtime specific, right? That's runtime specific. So today we just talk about like the Docker runtime, how we work around the Docker networking mode, right? And we are planning to support more runtimes, like for instance the Rocket runtime, and also the Linux container runtime. So make the container runtime more pluggable.
Just to follow up, if the two Docker containers running on the same port, right?
Yes.
They have the same IP address.
Yes.
But the code inside the Docker container doesn't know there's another container process share the same IP. Because if I write the code running the container, assume it's a host, right?
Yes.
How do you solve this conflict?
Then that's the user's job to define to define how you want to run your pod, right? You want to run the pod that makes sense, make the application that makes sense, that don't conflict within the pod.
So actually, also one container, one pod.
You can do that. Yes, you can do that. I mean, we didn't limit that limit. Yeah.
I wanted to just add some clarification to your question. The most important part of this slide is the and local host part. So the two containers within the pod are on the same local host. So they can always connect to local hosts on the port and talk to each other, and they get feedback. So essentially, that's to the other question, think of a pod, an analogy that one of our guys used. Think of a pod as the modern object-oriented language. Right? Today, everybody knows you make objects, you compose other objects together, and you make bigger objects. You make an API out of the bigger objects, right? You hide some parts of the smaller objects and you expose some parts of the other. When you build a pod, you're building a larger object out of smaller objects. So you take your MySQL container and your little MySQL helper container and put them together. If they both need to run on the same port, then you're in trouble because they need to work together. Right? You as the developer are building this larger object, so you need to coordinate those pieces together and produce your pod, which itself has sort of a crisp outer layer that is your pods together. Does that make sense?
The concept I would say that you are breaking the traditional like host and subnet with the coding pattern. For example, usually I have a little here with a backend of Postgres database. So if the Postgres running on one container, then the one on another, there are two different. Don't you?
I mean, sorry, you can do that. It's a perfectly valid pattern to take your VM, take a snapshot, run the whole thing in a pod, but I wouldn't do it. It's not the ideal way to do things. What I really want is to stratify the layers.
But I can say, for example, if you use Docker Swarm, you can do it.
Nothing, I mean, sorry, just to be clear, we should take this offline. Sure. Nothing that we're saying here means you can't do it. We're saying the system's built for pods, not one container, but one abstraction, one rule, one job, right? So it might be multiple containers that work together if they're doing one thing.
You know, that was my 2 cents on this, is that I always view a pod as a blueprint that you're going to be scaling horizontally. So you may have Nginx providing a front end for your Python as a service, and you have each one of these is separate to the same pod. You also have another pod that is providing stats. For that, something of that nature. This is a blueprint that you're going to put together across your infrastructure at scale as necessary. And in that blueprint case, you're always going to have Nginx running on the same port. You're always going to have that backend web service running on the same port because Nginx has to be able to talk to that backend web service. That is the notion I've always thought is for. It sounds like that's the thing. Having a complex application is going to have multiple pod specs to fund it.
We should take this afterwards. Yeah, it's a good conversation.
My question is related to the routing.
Okay.
You mentioned if you take solely rely on the external fabric for the routing or host level, you can do something with route to specific host.
Yes. So the question is, who does the routing, right? Who actually does the routing? So Kubernetes is not, its job is not for the routing. So it depends on the external support. So it can be the cloud provider that provides the programmable fabric, or some overlay like solutions. Like,
so the routing has to be done outside Kubernetes. It has to put in first before you start using it.
yes. Yeah.
Now, 3 questions back, I think the gentleman asked about containers, one container communicating with another container, and like there's a couple scenarios. One was when they're in the same pod.
Yes.
And you get all kinds of IPC,
Yes.
and all that. But when the containers are in different pods and they're communicating, don't you need to have a service defined first and then communicate to the service? Or it sounds like in your answer, there was some way that the pods could communicate, even if the containers could communicate. C1 is on P1, C2 is on P2. It can communicate even in the absence of a service. Which
Yes. That's
you
true.
can say more about that?
Yes, that's so pod and pod can communicate. So that's done here by the network fabric underlying. So it get routed to the host, and the host deliver to the Linux bridge, and the Linux bridge delivers to the pod. That's pod to pod, and you can also access the pod through a service. It doesn't limit to You can do both ways, pod to pod or pod to service. Oh, how to discover the IP? Yes. Yeah. It's either, so the IPs of the pod can go away at any time. So the client has to find out where the IP comes from. One way is through the Sky DNS, the DNS, kubedns we provide, but that's for the service. So it's not ideal to like establish a communication just to a pod. That's why we have the abstraction of service. Make sense? Yes. Yeah. Go through service. That's a static entry point. Yes.
So just to add to that, there is a whole class of applications that doesn't want to be load balanced, that wants direct access and is willing to deal with it's called the details of IPs changing underneath them. And for those applications, we actually have a different kind of service. We call it the headless service, which actually allocates, when you do a DNS lookup, instead of giving you a single A record of the virtual IP, it gives you back all of the A records of the actual IP, which means that over time, you're going to get different results. But if you're opting into that behavior, we sort of assume you know.
My question is about like the roadmap and the solutions around the DHCP. So I'm curious if I have a pod which has to get IP to the DHCP, but the DHCP server is actually running another pod. How is there any suggested solutions or solution for this?
Okay, so let me rephrase the question. So basically the question is how do we manage the IP for the pods, right?
How IP itself has to get, the pod itself has to get the IP from another DHCP server, which is
yes.
another pod.
So the beauty right now of Kubernetes right now is that the IP stays locally to a host. So we don't rely on the DHCP to get the IP from. So it can be just, we can track the, I mean, there's different implementations. The easiest one's just to track it with a file, or we rely on Docker. They have IPAM, so they manage the IP allocation for us.
Yeah, if we want to even our DHCP server, the solution we have our DHCP server.
So the answer here is your question. Right? I mean, the answer here is network plugins. Right? You're now outside of the normal, and you're into the custom. And so this is where building a plugin or using some combination of existing plugins is exactly what you want to do. If you want a plugin that uses DHCP, then you are responsible for the IPAM, and you are responsible for the routing. Right? So somewhere you've got to configure your fabric or something to do the routing. Maybe you have an L2 segment and you just arc it. That's all very, very specific to your installation. This is what network plugins are doing. So this is something that we're working really hard on right now. It's actually what we working on day in and day out.
Okay, yeah, thanks. The second question is curious about IPv6.
IPv6?
So she probably move on to the next stuff.
Yes.
Ina is going to be here, Tim is going to be here.
Yes.
Please can talk after. Also have one more quick question before you wrap up. Are there any tools that people can use today to set up Kubernetes clusters with their machines? Not necessarily Google Cloud or Amazon.
Like Flannel is one of the out-of-the-box network provider. And you can also, like, if you wanted to run a dev cluster, you can check out our Getting Started page. You can actually run a Kubernetes cluster inside a Docker container. It won't mess up with your local settings. So that's really nice to set up, get started with Kubernetes. Yes.
You can, of course, use Condu.
Yes. Yes, of course.
It is part of it.
Yes. Thank you.
Just a second, guys. Just being set up. Hello, everyone. Can you guys hear me? Okay. Thanks for coming. My name is Sukesh. I'm an engineer working on Project Contif. In this part of the session, I wanted to talk about Project Contif and how Project Contif integrates with Kubernetes. And my job is to convince you by the end of this presentation that Kubernetes plus Contif is the best platform for deploying your microservices application. So let me step back and take a step back in time and talk about what is it that we are trying to do here. 30 years ago, Cray Computers created a supercomputer called Cray 2. And this was a engineering marvel at the time. This had 4 CPUs operating at amazing speeds of 256 megahertz. And it had 2 gigabytes of memory, and it required a liquid cooling system, and it occupied a whole room, and it required an army of engineers just to program and operate. Right? Today, we all carry a supercomputer in our pocket. Right? This is more powerful than Cray 2 ever was. Today, we live in a world of abundant computing power. Right? We live in a world of abundant storage capacity and so on. In the world of abundant computing power, the thing you need to optimize on is very different. Right? The thing you need to optimize on is the developer productivity, not the efficiency of individual machines. So I just did a back of the envelope calculation, right? Comparing the cost of a developer versus cost of a machine. Right? It comes down to not the formula to one. Right? So I'm talking about machines that have 48 plus cores, and if you do the math, that's 5,000 cores, right? I guess let me say it differently. A single developer time is more valuable than 5,000 cores of CPU. Right? Let that sink in. Right? What you need to optimize is the developer time. Right? What you need to optimize is the DevOps time. Right? The most important commodity, so to speak, right? The folks at Google have a good way of expressing this. They call it the humans to machine ratio, right? Or humans to container ratio, right? How do you increase developer productivity? How do you increase this ratio, so to speak, right? There are 3 things, which are very promising in my mind. One of them is the idea of immutable infrastructure, that your infrastructure is just a stateless pool of resources that your application can consume. Right? The second thing that is interesting is this concept of container being this unified format for application packaging. Not only for application packaging, it's the primary way that the developers want to consume the infrastructure. Right? If you look at the argument of VMs versus containers, one way to think about it is VMs is the way ops guy wants you to consume the infrastructure. Here is a VM, go do whatever you want. The containers are the way developers want to consume the infrastructure. Right? That is, have my container, now build this immutable package, and go run it in consistent manner in different environments, right? If you think about what schedulers like Kubernetes do, that is, they obviously schedule your containers where the best resources available. If you look at it the other way, what they let you do is they let the developer consume the infrastructure directly. There is no middleman there, right? You didn't have to call anyone to create a container for you. You didn't have to open a ticket anywhere, right? All you had to do is create a pod spec and launch. Voila, you consume the infrastructure, right? The containers have become sort of the primary way for developers to consume the infrastructure, right? So, this is what increases your developer or DevOps productivity, right? And the third thing, of course, is the concept of microservices, right? The microservices have become the best way to sort of structure your software and structure your team, right? This all goes back to what Adrian Cockcroft and others say, Conway's law, small teams, two-piece teams, or whatever you want to call it. It's easier to communicate within the team, so create small microservices and have well-defined APIs consuming sort of talking between microservices, right? So I think those are the three things that really help you increase sort of your developer or DevOps productivity, right? So how does Contiv fit into all this, right? So we've been watching the space, and we could see Docker coming in and sort of really changing the space where you could just package your container and you could run it everywhere, right? And then schedulers like Kubernetes, Mesos, Swarm came in. It really made it easy for you to sort of schedule your jobs across your entire data center, right? So, and we were looking at these customers, and we could see that the container runtimes and schedulers are not enough. People needed more to sort of really deploy the application or to sort of operate the data center, right? One of the simple problems is a lot needs to happen from the time you rack your server till the time you can deploy containers, right? Someone just was asking about how do I set up a Kubernetes cluster, right? This is what what we call Contiv cluster management does. It does the node lifecycle management. Install the OS, provision the packages, make sure the system is healthy, monitor the health of the system needs services, and so on. It's sort of like a controller for your node, so to speak. The second problem, of course, is the problem of networking, right? As Min talked so elegantly, you really need IP addresses per container. You need those containers to be able to talk to the rest of the data center, be it bare metal or VM or what have you in the data center, right? And there's also sort of non-obvious problems around how do you solve the problem of sort of inter-microservices communication, right? How do you know what's happening in your data center? So we'll talk a little more in detail in the rest of the slides about content networking. And the third problem, of course, is the sort of the stateful containers and the problem of data management, right? It's a large problem. We're sort of taking steps towards solving it. In the initial version, we have a way to sort of pool all the storage resources across your data center and sort of provide persistent volumes for your containers, right? So with that, let me jump into sort of Contiv networking. So a little bit of word on Kubernetes plugin infrastructure, right? Kubernetes plugin infrastructure is really good. It's very open and very flexible, right? So what I mean by open is the network plugins have a lot of freedom to do what they need to do. The entire Kubernetes API is accessible for all the plugins. Right. The second aspect is the Kubernetes itself is architected as microservices. You can replace any part of the Kubernetes, and as long as you're maintaining the same API, Kubernetes just works fine. This really speaks to the sort of the cleanliness of architecture. Right? Really big kudos to Kubernetes team for getting this right. What we ended up doing was we did replace kubeproxy with our own implementation of load balancer, right? And Kubernetes just works fine because we are exporting the same API as what Kubernetes expects, and Kubernetes doesn't care. Right? This really one of the great things about Kubernetes, right? Now, as a Kubernetes plugin, we embrace all the networking concepts that Min talked about previously, right? IP addresses per container, the notion of services and service routing and service discovery and so on, right? So where Contiv adds value is when these container IP addresses needs to be visible to the rest of the data center, right? In GCE, of course, this works because GCE conversions of /256 for every VM. In traditional enterprise data center, what you need is a way to analyze these container routes for the rest of the network, right? So this is what Contiv does, and we have one of the sort of pure routed mode where we being the sort of the network plugin for Kubernetes, we take all the container IP addresses and advertise it to the rest of the network as sort of /32 traditional networking. If you're looking for sort of simple networking for containers, this is probably the best move to have, right? As in, this is native networking as good as it gets, so to speak. But enterprise data centers are often complex. They have different requirements. Often we see customers who have sort of legacy applications, legacy app servers, that have L2 clustering modes. We see people who needed, sort of multi-destination frames. If you have those requirements, we do support L2 mode. Right? Traditional L2 VLAN. Your container has an IP address and that's just VLAN. Right? If you have sort of legacy databases or VMs, this is the mode you can use. And then there are cases where you would need an overlay, right? If you have sort of multi-tenancy requirements, something like EVPN is the best solution for you. And we do support both sort of routed and bridged mode of overlays. And even if you're based in cloud, sometimes overlay is the only way. And some of the public cloud providers, all you can get is sort of IP-like communication between hosts. Right? The only way your containers can have an IP address is if you have an overlay between those hosts. Right? So we do support overlay modes for those purposes, right? And we of course integrate with some of the SDN solutions that Cisco has, and we have things like sort of full multi-tenancy and built-in IPAM and so on. So one of the things we did it maybe slightly differently from other networking plugin is we ended up building an open flow-based switching pipeline in the plugin. Very high-speed switching pipeline that can operate at tens of gigabits per second. If you look at our performance numbers, they're almost same as bare metal Linux, right? Maybe 1 or 2% less than bare metal Linux. And what this allowed us to do is we have a very flexible switching pipeline. We can do sort of IP routing and sort of security policies, L4 load balancing, and some sort of telemetry, all in a single switching pipeline. Right? Just because it's a fully programmable, it's very easy for us to add new things. Right? just as a data point, someone in Cisco took Contif, and they were able to add MPLS and segment routing, just in a couple of weeks, right? That's the kind of flexible pipeline we have. And finally, of course, we build content networking for microservices, right? Modern applications are microservices style. So, what does it mean, right? We have sort of segmentation per microservice, right? You can say, microservice A is in one segment, microservice B is in another segment, and you can have policies that say which microservice is allowed to talk to which other microservice. And we do support service discovery and routing, which is L4 load balancing, as I talked before, right? We were able to replace kube proxy with our own implementation of L4 load balancing. And we do support, some of the application visibility and telemetry features. Just because we are sitting in the data path of every communication that's happening, we can collect a lot of data, right? So that's one of the benefits of having this very flexible programmable pipeline in the kernel. So let me dig a little deeper and maybe sort of go through the architecture of it, right? So what we have is a Contiv master component. Of course, I'm not showing Kubernetes here. There is Kubernetes and kubelet in this cluster, obviously, right? And I'm just focusing on the Contiv part of it. Question, right?
Can we use it with plain vanilla Docker?
Oh yeah, good question. So Contiv networking supports Kubernetes, Swarm, Mesos, or just Docker if you want to use it that way. We support all 4 major schedulers, including Nomad. Or if you just want to use it with Docker itself, you can use with Docker itself. We support sort of all the L3, all of them so we have a what we call a Contiv master component. This is where you would specify your policies. What we call operational intent, right? All our APIs are the desired state style. As in, you only need to specify what is your desired state, and Contiv figures out how to get to that desired state. And the master component is clustered. If one of them fails, everyone will take over. We use etcd console for storing all our state. And we have an agent component that runs on every one of the nodes. And there is a data path that's inside the kernel. And the data path is the one that's sort of providing these NetDev interfaces that go in every one of the Docker containers, right? And since we do IPAM for all these interfaces, every Docker container has an IP address. We'll probably look at some of this in the demo. And finally, we have this collector cluster. Which is, all it's doing is collecting data from all of the nodes, and it's always on, right? This is the telemetry aspect of Contiv, so to speak. Any question on the architecture aspect of it before I move on? Yes.
My question is how the parts of the Contiv solution are they themselves containerizable?
Oh, good question. So all the parts are containerizable. We're in fact in process of containerizing them, including the agents and the master. The data path itself, since it's in the kernel, cannot be containerized, but it's something that we can just mod probe. Right? Our agent can run in a container, and all we have to do is mod probe the sort of the KLM into the kernel. But the rest of it is fully containerizable.
So do you use daemon sets to install your Kubernetes?
We don't today, but it's so we have tried containerizing before. So one of the problem was, when you do Docker RMNSRF, everything goes away, right? So oftentimes we ourselves would do Docker RMNSRF and our agents are not, right? So unless there is a concept of infra containers. This is where Kubernetes and others are getting to, right? Where there is a certain containers are treated special, so to speak, right? Which cannot be removed by the regular users. That would be something interesting to use.
Also, any plans to integrate with OpenStack?
There's no, never say never. Not right now, but it's an we are developing a sort of what you call lean startup way, right? That is, you develop the minimum viable product, take it to the customer, and anything else has to come from the customer. Right? So if there is enough interest on OpenStack from customers, of course, it's something we'll do. Now, having said that, I think containers on bare metal is much more interesting value proposition than containers on OpenStack. That you really get the benefit of sort of having that low overhead. You don't, especially if you're sort of Linux application running in Linux hypervisors, including ESX, which is Linux hypervisor, right? There is no reason for you to have Linux at all, right? So you're better off running containers directly on bare metal. Personally, I would prefer people use containers on bare metal, but there are cases where it's not feasible, right? Like service providers or cloud providers is one such example, where you probably do need some VM of some sort. Let me move on to the sort of the main thing I wanted to. Okay, I think the picture isn't clear at all. Anyway, so when you're moving from the monolithic architecture to microservices architecture, you're fundamentally building distributed systems, right? I mean, by definition, right? And the distributed systems interact in complex ways, especially when these distributed systems are being scaled independently, upgraded independently, right? And version controlled independently. The interactions can be very, very complex. The picture that's not showing up is actually a microservices architecture from Twitter. Let me see if okay, it's still not visible. Okay, where they have 500 plus microservices, and there is API calls between n number of microservices to n other number of microservices. And each of these microservices are scaled independently, right? In such a complex system, one of the fundamental things you need to know is what is happening in your data center, right? Now, if you step back and look at it, sort of the REST or the RPC has become the de facto standard for communicating between microservices, right? Google famously has single RPC library in their entire data center. Twitter has Finagle, Netflix has Vipin, and every enterprise has some variation of this RPC library, right? And they're making calls, and often these are nested calls, right? You visit, say, Amazon.com, it's making up to 150 calls, which in turn are making probably tens of calls to other backend systems, right? So in that world, sort of having the visibility of what is happening, right, is very important. And now, because networking is in the path of these RPC calls, as I mentioned, Contif has a kernel component that's sitting on every server, and every one of your RPC calls are going through the Contif networking component, right? And there is a lot of data we can collect because we are sitting in line, right? There are very simple things we can provide, things like connectivity maps, right? Which microservice is talking to which other microservice. We can do things like, historical data, right? Because networking is always on, and because we are sitting in the sort of the inline of the RPC communication, you don't need to instrument your code, right? You don't need to instrument your Java libraries. You don't need to run agents on sort of every container as sidecars or whatever. We can have these logging always enabled, right? You can use it for performance tuning. You can use it for audit trail purposes. Your target, someone hacked into your database. You want to go look at where did that access come from, right? Having sort of this always on logging really helps in those databases. All you have to do is sort of log all this into a big Cassandra style database, right? And you can almost keep it forever. So I guess some of the telemetry data collections that we could do is, I'm not really going to go through each one of them. These are some of the things we could collect. Generally, we collect sort of L4 level statistics. We don't go L7 because for performance reasons we don't want to see beyond TCP, right? We don't want to intercept sort of every one of your REST calls in that sense. And the challenge of analytics and making sense of this data and visibility is something that we're still in early stages of exploring. And you can see we're just scratching the surface here, right? So with that, let me sort of jump into a demo where I can demonstrate some of the visibility aspect of content, right? Of course, I could demo the L3 routing or service routing. This is sort of you would see everywhere, so to speak. And telemetry is something that's probably a little bit unique to us. So what I have here, let me jump to the demo. I have a simple Kubernetes cluster here. So I have one master node and two child nodes. So I have this idea for an application. I think this is going to be a really cool application. This application is on-demand taxi hailing, right? I'm sure no one has thought of it. Yeah, I'm sure no one has thought of this idea before, and this is going to be really huge, I think. So let me show sort of the pod specs of this application. Since this is Kubernetes Meetup, I'm going to call this app Kuber, right? Sounds very original, right? So what I have here is, let me launch the application first, and we'll go back and see the pod spec. So let me sort of bring up the topology of my so-called Kuber application, right? So what I have is 4 microservices. There is a passenger app, there is a driver app, trips app, and a payment app, right? And I have a web tier that's load by, sort of front-ending and aggregating all these tiers. And I have 2 instances of database tier, 4 instances of application tier. This is 4 pods or 4 containers, and I have 8 instances of web container, right? So let's quickly look at some of these pod specs, right? So let me open, say, so this is my passenger app. So I'm saying there are 4 replicas in this app, and I'm just using some Python application to run connection to a Redis database, right? And so the second thing is let me increase the size. If you see, I created a service for every one of my apps. There is a passenger app service, right? So if I look at the passenger app, you would see there are 4 instances of these pods, right? Which is front-ended by the passenger app service. As I mentioned, we take the Kubernetes service concept, but implement the load balancing ourselves in our unified switching pipeline, so to speak. And if I look at the replication controllers, right? This is what is controlling one service, right? Passenger app is one service, but there are 4 instances of this pod, right? So let's go to our UI and see how we can see all this coming together, right? So we have a little UI here, right? So let me show. Let's see if I can align all this. So display is really not helping me. Let me see if I can decrease the brightness maybe. Okay, so oops, I just lost my display. Okay, much better. So you can see the lines here, right? And what I'm showing here is there is a single web service, right? There are 8 instances of this pod running, but I'm only showing a single web service here, right? It's talking to 4 apps, right? One is the passenger app, the driver app, the trips app, and the payments app, right? And each one of these services have a backend database, right? The trips app is talking to trips DB and so on, right? The thickness of this lines here indicate how much traffic is flowing, right? Between these tiers, right? So let's zoom into one of the apps, right? Let's see the actual instances inside this, right? You can see here I have 4 instances. Let's see if I can. Okay. I have 4 instances of trips app. That's the blue circles at the bottom, and that's talking to sort of the 2 instances of the database app. That's on the right. And you can see the content load balancing kicking in and balancing traffic across all those, right? And you can see the same. I have sort of these 8 instances of web tier in the top, and you can see this traffic is load balanced to all 4 apps instance of trips app, right? I can do the same for maybe one of the other apps. So let's see who's talking to payments app, and you'll see the same picture, so to speak, right? There is web tier, right? That's talking to the 4 apps tier, 4 instances of app tier, and then they're talking to the payments database, right? Now we constructed this all live, right? I didn't have to construct this graph. All we had to do was collect the data that our telemetry engine is providing us and visualize it, right? That's all we had to do. Now, so let's say I have a problem, and I want to look at sort of how much traffic is going on between my driver app and driver DB, let's say, right? So all we have to do is sort of click the link, and this is in the early stages. It's very raw UI. Pardon me for showing very simple graphs here. But you can see sort of the traffic that's going on between my payments app and or my driver app and the driver DB, right? So sort of that's very very quick demonstration of how network being in that path of RPC calls can enhance sort of the developer's life as well as operator's life, right? You get a much better visibility of what's happening in the network, right? Not only you can see sort of port level statistics, you can see service to service or instance to instance level statistics. I think with that, my little demo concludes. Thanks everyone. If there are any questions, we'll take at this point. Yeah. Thank you.
Great presentation. Before we wrap up, we also have a whiteboard. This runs Docker and Kubernetes meetups in India. He's worked with a few more people who have used it on networking, like Jain networking.
Something that we can do. Now I understand why you kept training coming for Angular JS. Refresh not happy.
Belt packs back here. Yeah. Just pull it up. Pull it up. Yeah. So, was it on? I didn't realize. No. Thank you. No, it wasn't on. We brought it down when we left the stage.
Okay.
Pretty weird.